We've talked about functions represented by graphs, functions represented by tables and by formulas, and now we look at functions represented by words, and there's going to be lots of words in this section. I love that classic song from My Fair Lady. Okay, let's get started here. So here's our first example. Net sales of iPods rose 3.2 billion during 2005 compared to 2004. Unit sales of iPods totaled 22.5 million in 2005, up from 4.4 million iPods units sold in 2004. iPod sales revenue was 1.3 billion in 2004 and 0.9 million iPod units were sold in 2003, generating 0.3 billion in revenue. Predict sales revenue when 15 million iPods are sold. So this is typical of a problem where we're thrown a bunch of words, and from it we have to answer a question related. There really is a hidden function in here. We've just got to tease it out and then do the prediction that they ask us to do. There is a model, a mathematical model that we've got to figure out from all these words. And my favorite way to do it is to take the data and put it in a table and see what we can see. So how do I even know what to put in a table or how to put it in a table? I look at the question that they are asking us. Predict sales revenue when 15 million iPods are sold. So in all of this, there's sales revenue going on. I've seen that a couple times. And then there's number of units sold that keeps coming up different places. So sales, units sold. There's also a bunch of dates in here. So there's really three different quantities that they're talking about. But when in the question they ask us to predict sales revenue, using the word predict means this is an output. This right here is our output unit, sales revenue. And the tip-off is the word predict. So predict a certain sales revenue when 15 million iPods are sold. This tells us that the number of units sold is our input variable. So when you know this about how many are sold, can you predict the sales revenue? Okay, so that's a starting point. So I've created a table, and just like we were saying, I know my input value or variable is number of units sold, and I'm going to call that N for number. That came from the prediction was based off of how many were sold. And my output is revenue because that's the thing that we're trying to predict. Now we're just going to dive into this paragraph and see if we can fill this table in. And the very first thing I come to is net sales of iPods rose 3.2 billion during 2005 compared to 2004. Okay, I'm going to hold on to that for a minute because I don't see anything really obvious yet. Unit sales of iPods totaled 22.5 million in 2005. That's a good piece of data right there. So we're definitely dealing with 3 years. We've got 2003, 2004, 2005. So even though the years are neither an input or an output, I'm going to put them by the table just to help me organize things. Okay, back to all these words. The first sentence really just gives me a comparison between 2005, 2004. I'm going to hold on to this for a minute and wait on it. But the second sentence, unit sales of iPods totaled 22.5 million in 2005. That's something I can put in my table right now. So in 2005, 22.5 million iPod units were sold. And then in the same sentence, it tells us that was up from 4.4 million iPod units sold in 2004. And so I know also that in 2004, there were 4.4 million units sold. Okay, the next sentence has a bunch of info too. iPod sales revenue was 1.3 billion in 2004. Great. Okay, so revenue in 2004 was 1.3 billion. And right now we're going to go up here and indicate that this is in billions, units sold, or revenue, sorry, and then units sold, this is going to be in millions, these numbers. And there's still some more info in this sentence here. So we got the 1.3 billion in 2004 of revenue. And then it says, and 0.9 million iPod units were sold in 2003. Okay, so in 2003, 0.9 million units were sold, generating 0.3 billion in revenue. So the revenue in 2003 was 0.3. Okay, we've used all the information from these two sentences. We need to go back and pick up what was going on in that first sentence. Net sales of iPods rose 3.2 billion during 2005 compared to 2004. So whatever the net sales revenue of iPods was in 2004, in 2005 it was $3.2 billion greater. And so this 1.3, we're going to add to it 3.2, and in 2005, we know that it was 4.5. And that's billions of dollars. So we should go up here actually and say that revenue is being described in billions of dollars. That's the true unit of revenue. So we've done a lot of the work to take all of these words and get them into a table of data. And now our job is to predict the sales revenue when 15 million iPod units are sold. We don't have 15 in our data set. It's sitting here between 4.4 and 22.5. What we'd really like to know is what revenue was when 15 million units were sold. So we're going to use the average rate of change like we did in the last section. We're now going to find the average rate of change between these two data points, and that will help us predict how things are growing between these two data points, because we're really interested in being able to extrapolate to predict a number that's in between these. So take that average rate of change and kind of build on it from here to predict what's going on with revenue. So we start by finding the average rate of change. And so I'm remembering this is the formula for average rate of change from a couple sections back. The difference of the outputs over the difference of the inputs. So I have 4.5 minus 1.3 for my numerator. And then I have 22.5 minus 4.4 for my denominator of my average rate of change. So the number I get is 0.178. And just as importantly, we want to figure out what the units are. It'll be billions of dollars per million units sold. So this is such an important number to understand. This is telling us that around this area, when we sell 1 million units, we can expect the revenue to go up this many billion dollars. And so as we're trying to build to, well, what happens when you sell 15 million units? We're going to be using this number. So for every million units sold, you can expect your revenue to go up $0.178 billion. So I just restated that here. When we're growing from between 4.4 to 22.5 units sold, every time we jump in 1 million units sold, revenue grows on average, because this is an average rate of change, $0.178 billion. Okay, so we're trying to grow from 4.4 to 15, and that is going to be 10.6 million units that we're growing in this interval. And so we're going to use that 10.6 and knowing this number here to build what revenue should be. So we're really interested in knowing what's going on when 15 million is our number of units sold. And 15 million from 4.4 is 10.6 units. We also know for every 1 million units sold, as we go up, every 1 million increase in units sold, revenue goes up, this 0.178 billion. Well, we've gone up 10.6 million units sold, so we can expect that revenue will go up 10.6 on average, 10.6 times this number. We're not going just 1 million up, or 2 million, or 3 million, or 4 million, but we're going 10.6 million up. And so it's that many times this 0.178 billion. Now I'm going to write this using function notation. They've asked us for the revenue when 15 million units are sold. And so we've decided to use average rate of change and say that, well, the revenue when 15 million units sold, the best prediction will be the revenue when 4.4 million units are sold, plus this 10.6, so climbing up to 15 times how much it grows on average between those for every million units that we sell, which is 0.178. So we're asked to predict the revenue when the number of iPods sold is 15. We're going to take the revenue when 4.4 million units are sold and build off of that. We know that it's growing at this rate right here for every million units sold. Between 4.4 and 15, we have 10.6 million units being sold. So we need to multiply these together to catch all of the growth. This is the growth per million, and we have 10.6 million between 4.4 and 15. Okay, this is a lot to take in. So, you know, make sure you're thinking kind of slowly what is going on in this. But this is a great problem because it's incorporating a lot of topics that we're talking about. So this is sort of the key idea right here. So, you know, feel free to rewind and watch again and kind of think through this whole problem. We're not even done yet, but we're kind of, this hard work right here is done. From here, we're just going to get a number and we'll interpret it. But this is really the key idea and the key logic behind everything. So now we'll find this number and be able to answer their question. The revenue when 4.4 million units are being sold is 1.3 billion. So this number is 1.3 billion. Plus to that, we're going to add 10.6 times 0.178. This was what we built, what we're building up from 4.4 up to 15. And this number is 1.89. And when we add those together, we get 3.2 billion, which sounds pretty reasonable, just looking at the table. So this is our solution, that when we have 15 million units sold, that our revenue would be 3.2. And we just built this number off of this one and using the average rate of change. So we're done. We do have our answer right here, but I do want to look at the graphical representation of what's going on with these inputs and these outputs. On our horizontal axis, we have the input variable n, the number of units sold. Our vertical axis, we have the output variable r, the revenue. And if I were to plot the point 4.4, 1.3 on my graph, let's see, that would be, this is 5, 4.4, 1.3. It's about right here. And then 22.5, 4.5, 22.5, and 4.5 maybe is about right there. This is how things are growing between 4.4 and 22.5 units sold. So if I go to an input value of 15, and my graph is right here, so 3.2 isn't a reasonable estimate for the revenue. And I can see that graphically, but we did it algebraically using average rate of change so we could get a more precise number. Definitely lots to think about in this problem. I want to give you some common phrases that you might come across in some of these problems and how to tell what's an input and what's an output. Whenever you see something as a function of something else, this first word, whatever it is, this is your output and this is your input. When you have some output as a function of, and then this is going to be your input. It might be something like salary as a function of hours worked. But when you see this phrase as a function of, the thing that comes first is your output and the thing that comes second is your input. And you'll see that phrase. Another phrase you might see is the phrase that models something, like that models revenue, that models population. And whenever you're saying modeling something, this again is an output. We saw in the last example that they asked us to predict revenue, and so when we're asked to predict something, this is generally the output of your function also. So these are some phrases we may see in a typical problem. They may not tell you, oh, and this is your input variable and this is your output variable. But they'll give us some clues in the context using some of these phrases. I thought of one more phrase that we're going to see, and we'll actually see it in the next example. when something is based on something else, then this first thing is your output. We're going to see in the next example a weekly paycheck based on the number of overtime hours. And this will be your input variable. Here's our next example. In 2011, minimum wage was $7.40 an hour. A worker in Michigan gets paid time and a half for any hours over 40 hours per week or overtime hours. Create a function to represent his weekly paycheck based on the number of overtime hours he worked. Okay, so this time we don't need to just find one certain data point. We're asked to create the function. And so I'm going to go back to a table. I love making tables, and I'm going to try to get some of this information and get figured out what's the input and what's the output. So we were just talking a minute ago how the phrase based on will give us a hint as to what our output and what our input is. And his weekly paycheck is based on the number of overtime hours he worked. So weekly paycheck is going to be our output. So weekly paycheck is the output in our table, and the input will be the number of overtime hours he worked. So we've got number of overtime hours in the table as an input variable, and we'll call that variable H for overtime hours, and the output variable is going to be P. We're asked to create the function, so we need to come up with a formula for this function. And really the only information we have is that the worker is paid $7.40 an hour. So we're going to have to construct some data based off this information. And the first thing we think about is, okay, well, what if, say, he worked actually 0 overtime hours? Let's start there and see what his weekly paycheck would be. So if he worked 0 overtime hours, his weekly paycheck would just be his hourly wage, $7.40, times the 40 regular hours that he worked, and that will be $296. So he worked 0 overtime hours, he gets $296. What if he worked 1 overtime hour? That wouldn't be too hard to calculate. So if he works just 1 overtime hour, he's going to get his regular paycheck, just the $296 for his 40 regular hours, plus he's going to get 1 times time and a half. So what is time and a half? It's 1.5 times 740. And 1.5 times 740 is 11.10. So 1.5 times 740 is our time and a half rate, and that's 11.10. And so that week, his weekly salary will be $307.10. So 307.10. And from this we could kind of start to see how a pattern might emerge, but let's go ahead and get one more data point. So if the worker works 2 overtime hours, we could expect again his regular 40-hour salary plus 2 times the time and a half. And that would be $318.20. So for 2 hours of overtime, he's going to make a weekly salary of $318.20. And I do start to see a pattern emerging. You know, they didn't ask me to come up with these data points. They just asked me to come up with the function, but I knew I couldn't just jump into and figure out what this function was. I needed to wrap my head around what was going on. And so at this point, I can start to think, well, what if he works H hours of overtime? What would his weekly paycheck be? And I can see that you just take the base salary, the $296, plus however many overtime hours times 11.10, and that will always give you your weekly paycheck. So now I'm ready to come up with a formula. Now I can see that when I work H overtime hours, my weekly salary is $296 plus that H times 11.10. And so I'll go ahead and write it in function notation. And here is the answer to the question that they ask. P of H, so paycheck as a function of overtime hours worked, is 296 plus H times 11.10. So importantly in this example, we learned that sometimes it's good just to create a table and try to get some data points to figure out what's going on, what the underlying pattern is. Even though they don't ask you to do this, it's a good idea almost always to make a table and get an idea of some of the data points. We have one last example for this section. It's a really great example. Okay, so this big honkin' long formula, this function gives the number of golf courses in the United States as a function of years since 1990. So as a function of, that was a phrase that we needed to look out for. And that tells us that this is our input, years since 1990. So that's time right there. And it gives the number of golf courses in the United States. So that's our output. And that's the G of t. And that's what this big whole humongous formula does. Oh, I see an error right here. We need to make sure that this is not an X, but that it's a T. So I'm going to change that to be a T. Okay, so the formula basically says you give a year, T, and if you plug it in right here and do all these calculations, that out of this formula spits the number of golf courses in the United States. And then we're asked to find and interpret G of 18. So one way to do this is take 18 as our T, and we could plug it into this formula and calculate all this stuff. And that's totally valid. You can do that. This is, we're going to illustrate something else in this example. We're going to do this sort of graphically using Desmos. So what we have here is, I went ahead and put in the function into Desmos. Looks like it's truncated a little bit. The other number is really there. It's just maybe not a big enough screen, but the 12,000 is sitting right here. Okay, so I put this function in and I used X and Y's as my input and output because Desmos prefers us to use X and Y's. And this is what the function looks like. So our input variable is years and our output variable is number of golf courses. I did have to change the dimensions of my graph to get a good picture of it, and you can do that using tools, and you can change like what the x-axis is starting and stopping at, and the y-axis I knew it needed to be probably bigger than 12,000 because that was one of the big numbers at the end of the formula. So just know that this tools icon can help you scale things on your picture. Okay, anyway, if I have this graph and I want to know what's my output when my input is 18, I can actually put in a vertical line, x equals 18. And what that does is this will spit out the answer for me. If x equals 18, then I can click right there and find out what that point is. And it says that when x is 18, the output of this function is 14,912.888. So I don't even have to calculate anything. I can graphically and using Desmos find that point. When x equals 18, what's the output value of the function? So this is now another tool that we have in our toolkit that we can take a function and graph it and get some information that we need. We can do it algebraically, but you can also graph it and find output values just from the graph. And Desmos is so powerful. Let's do another one. So no, that's wrong. Before we do another one, we need to finish this problem. We found G of 18, but now we're going to interpret it. What does it mean that G of 18 equals 14,912? Well, it means that 18 years after 1990, there are 14,912, maybe 913 golf courses in the United States. And so it's important to write that out as the interpretation. So the meaning of what we found is that in 2008, which is 18 years after 1990, in 2008, the model predicts there are 14,912 golf courses in the U.S. If you'd said 14,913, that would have been an acceptable answer too, somewhere in that range. Let's just do another one to make sure we got this down. Find and interpret G of 11. So we're going to go back to Desmos and do this. And this time I'm interested in when my input is 11, what is the output? So I'll find the point of intersection for x equals 11 and this function right here. And it looks like it's 11,13,015.704. So here we have that when x equals 11, or when t equals 11, when our input is 11, then our output, G of 11, is 13,015. So this time I just rounded to 13,016. And the interpretation is really similar. It's just 11 years after 1990. So in 2001, the model predicts there will be 13,016 golf courses in the U.S. Okay, last question. Find t for when g of t equals 12,100. So this time we're looking for the input value and they give us the output value. So we're going to use Desmos again. This time as we use Desmos, it's the output that we know. So it's in Desmos, the output is y. So it's the y value that we know, that it's 12,100. And we get this, well, it's really tight in there. So I'm just going to use my, whoops. Not going to do that. So y equals 12,100, and I'm interested in that point there, but I'm just going to kind of expand things a little bit, open it up to see what's going on. And it looks like that point is really close to 0, but it's 1.0912,100. Okay, so let's go back and interpret that. So here it is. When my output is 12,100, my input is 1.09. So what that means is if g of t equals 12,100, then I can tell graphically that t equaled 1.09. I'm going to tell you this is a real advantage using the graph instead of the formula in a case like this. To solve the equation 12,100 equals all for little tiny little t right here, that's a lot of algebraic work. So in this case, it worked out really well to graph the function and read off information about the function from the graph. It could have been done algebraically, and as we practice, you'll get you'll get more skilled at knowing when to use a graph and when to use algebra. But I love using graphs. I feel like I can get a real sense of the function and get a lot of data out of graphing the function, and Desmos is so good about giving us specific values. They didn't ask us to, but we'll go ahead and interpret the meaning of this answer. When there are 12,100 golf courses in the U.S., the model tells us that it's 1991, that it's 1 year after 1990. Some of the things that we were able to do today are we were able to take a lot of wordy problems and get the information out of them into a table and then sometimes construct a function. We were also able to get more practice using the average rate of change in that example one, and a lot more practice using Desmos too. So a great section.